Hello everyone, so welcome back to another video of the S block elements, and that is going to be with respect to the important compounds of alkaline earth metals. So for today we are going to discuss about the compounds of alkaline earth metals and which are most important for your annual exam point of view. We are going to take a look as how these particular compounds are prepared, what are its properties and the uses. Okay, you can expect these particular questions in your examination in a subdivision of 3 or 4 marks. Alright, so let's get started by one. So first one, as we start with calcium hydroxide. So calcium hydroxide, it is also called as slate lime. Okay, so now first thing that we have to understand is what is its chemical formula. So when we take a look into the chemical formula here, it is represented as CaOH twice. So this is our chemical formula. Now why is it CaOH twice that you have to think? Okay, now here when we observe calcium is in the form of Ca plus 2, right? While OH has a charge of minus 1. Okay, so we write it as minus 1 here like this. So this is for plus 2. Now what shall we do is, we simply cross multiply this along with its magnitude, that is Ca1OH twice. So CaOH twice. This is how we give the formulas. Okay, so now taking a look into the preparations. So when we observe about the preparation of this particular compound, that is the slate lime or calcium hydroxide, we prepare this compound from calcium oxide. Okay. Now this calcium oxide, as what we have, is also called as, we call it as quicklime. So calcium oxide, as what we have, when we take this calcium oxide and as we react this calcium oxide with water, okay, as we react this one with water, we get a compound that is going to be slate lime. Okay, it is going to react and it will give us CaOH twice. Let's observe two hydrogens, two oxygens, one calcium, perfectly balanced. Okay, so this compound over here, as what we have got, is nothing more than the slate lime. Okay, now taking a look into its properties. So when we observe about the properties of this calcium hydroxide, first thing that we have to understand is calcium hydroxide is a white color powder. Okay, it is a white color powder. And when we take this calcium hydroxide and we put it into water, okay, as we try to dissolve this into water, what we understand is, as we put this into water, this is sparingly soluble. Okay, it is going to be sparingly soluble, slightly soluble. Okay, and as we try to do that, when we put this powder into water, okay, as we put it into water, what will happen entire thing becomes a particular solution, and this solution which we get upon addition, already we know that this thing is sparingly soluble. That means there are particles which are quite visible to you. Okay, and this solution which we get upon addition of calcium hydroxide in water, this solution we call it as lime water. Okay, so this is called as lime water, and only the liquid form. If you observe only this liquid over here, which is usually called as suspension. Okay, this suspension as what we are getting here, this suspension is called as water of lime. Okay, so this was about the property, the first property of calcium hydroxide. So calcium hydroxide is a white color powder which is sparingly soluble in water. As when we put it into water and stir it well, it gives us a solution. That solution we call it as lime water. The suspension, only the liquid layer, we call it as water of lime. Okay, so we'll observe the next one. Coming towards the second property. So property number 2. So we already know that when we take calcium hydroxide and when we put it into water, it gives us a sparingly soluble solution. Okay, so when we supply, as we pass, or we can say as we pass carbon dioxide gas. Okay, as we are trying to pass the carbon dioxide gas in the solution of calcium hydroxide. Okay, what we observe here is that this particular solution of calcium hydroxide turns. It turns. What is happening is it is turning milky. Why it is turning milky is because it is going to give this particular carbon dioxide on reaction with calcium hydroxide gives us a precipitate of calcium carbonate. Okay, we'll observe the reaction of calcium carbonate and it occurs something like this. So CaOH twice plus carbon dioxide, and it is going to give us calcium carbonate along with elimination of water molecule. So this particular thing, what is formed is nothing more than the white precipitate. Okay, that means it is responsible for creating the entire solution milky in form. Okay, so what we have done in this entire scenario here is that you had a solution. Okay, there was a solution of calcium hydroxide. To this particular solution of calcium hydroxide, we have inserted a pipe, and through this particular pipe, we have seen that we are going to pass carbon dioxide gas. Okay, so when this carbon dioxide gas moves inside, it reacts in order to give us a milky white precipitate. Okay, so it generates white precipitate, due to which this entire thing becomes a milky white in appearance. Now, as we travel to this next one here, as we take this particular white color precipitate and as we pass excess amount of carbon dioxide. Okay, so when excess amount of carbon dioxide gas is passed through the solution, okay, this milky white solution now becomes again colorless. Okay, so therefore the solution turns colorless. Alright, so it's going to turn colorless from its milky appearance. Now again a transition, colorless from the milky appearance. Okay, now we'll observe why is it happening so. Okay, so as we observe over here, we already have calcium carbonate, and this calcium carbonate is going to react with carbon dioxide under the presence of water. Okay, under the presence of water. Now what is going to happen is, as it starts reacting, okay, this particular white precipitate which was responsible for generating a milky white appearance will react with carbon dioxide under the presence of water in order to give us calcium hydrogen carbonate. Okay, this calcium hydrogen carbonate, this is quite soluble in nature. As this particular compound is soluble in nature, again the white precipitate is converted into colorless solution. Okay, so this is how it works out. Let's observe if the entire things are quite balanced. One calcium, one carbon, so therefore we have two carbons on our reactive sides, so therefore two carbons, right? The number of oxygens as what we have is 2 over here, plus 1, 3, 3 plus 3, 6, so 3 into 2, 6, perfectly balanced. Okay, so therefore this is how it should have been. Now coming towards the next one, as we take this particular calcium hydrogen carbonate, solution. Okay, now this is also called as calcium bicarbonate also. Okay, so this solution as we take, and if we heat it, what will happen here is this calcium hydrogen carbonate will get decomposed. It is going to get decomposed, it breaks down. Okay, it breaks down in order to give us back again calcium carbonate. That means the solution again turns milky on heating. Okay, when it is heated, it decomposes to yield calcium carbonate, which is again milky in nature. Okay, so again it is going to be milky in nature. That means the solution turns again milky in its form. So therefore, as we observe this calcium hydrogen carbonate, when we take it and as we heat it, what is going to happen is the calcium hydrogen carbonate changes itself into calcium carbonate. Along with this, there is an elimination of carbon dioxide plus water molecule. Okay, so this is how the reaction occurs. Now, here what was happening is that the milky solution was getting converted into colorless solution, while here the colorless solution was turning into milky white as we started to heat it. So these are particular properties. There is one more property which we will see soon. Moving forward with the next property, and that is when the calcium hydroxide reacts with chlorine. Okay, when this thing reacts with chlorine, this thing produces a hypochlorite. It is a hypochlorite. It is a very important component in disinfectants or in bleaching powder, you can say. So therefore, it is a very important compound for disinfections. Okay, so when we have this calcium hydroxide reacts with chlorine in order to yield a byproduct calcium chloride. Along with the byproduct is our main product, and that is going to be calcium hypochlorite. Along with this is the elimination of water molecule. Okay, so it is going to be a very important reaction for us. Now, coming towards the next section, and that is going to be uses of calcium hydroxide, or also what you call it as slaked lime. So the first use of this, the first and foremost use, is in the preparation of mortar. Okay, so mortar is nothing more than a combination of slaked lime along with silica in a perfect ratio. Okay, so this mortar usually is a combination of slaked lime with silica. Okay, in ratio of 1:3 or 1:4. Okay, and this particular mortar is a very, very important building material. Okay, so preparation of mortar is used in building materials. So therefore, how it is prepared? It is prepared by a combination of slaked lime with silica in a ratio of 1:3 or 1:4. Okay, so now coming forward with the next use, and that is going to be, it is used in whitewash. Now, whitewash is because of its disinfectant quality. So therefore, because of the disinfectant quality, we are going to use this particular slaked lime in whitewash. Next one, it is used in glass and tanning industries. Alright, so it is used in glass and tanning industries. It is used as disinfectant and also in purification of sugar. So these are the uses of the slaked lime. Okay, so we have the 4 uses. You can expect this particular thing in your examination. So let's go further. Moving with the next one, and the next important compound as what we have is the plaster of Paris. Okay, so when we are taking a look into the plaster of Paris, first thing is about its chemical formula. So as we take a look into its chemical formula, it is CaSO4 dot half H2O. Okay, so this is the chemical formula. In simple terms, between 2 calcium sulfates, there is 1 water molecule. Okay, so 1 calcium sulfate will have half water molecule. Simple as that. So therefore, we also call it as calcium sulfate hemi refers to half, hemi hydrate. Okay, so this is the name, the scientific name of plaster of Paris, and that is calcium sulfate hemihydrate. Now, as we take a look into its preparation, let's start with the first one, and that is going to be the preparation. So, under the section of preparation, we need to understand that this particular calcium sulfate hemihydrate is prepared from gypsum. Now, gypsum is again calcium sulfate salt itself, but it is CaSO4 dot 2 H2O. That means it is calcium sulfate dihydrate. Okay, so we are going to take this particular gypsum salt, and what we do is, as we take this CaSO4 dot 2 H2O, and as we heat it, okay, the temperature should be set at 393 Kelvin only. Okay, now when we have this particular thing, gypsum salt, and we are heating this gypsum salt will lose water molecule in order to give us CaSO4 dot half H2O along with liberation of water molecule. In order to balance this particular equation, let's say that we have here as 2. Okay, so therefore 2 into 2, we have 4 water molecules. Now these 4 water molecules will lose 3 water molecules here, and what we get is 2 calcium sulfate dot half H2. Now, taking a look into this particular water molecule. Okay, this water molecule over here, as what we write it as CaSO4 dot half H2O. Okay, now this particular half H2O, or whatever the H2O is remaining here, this particular water is called as water of crystallization. Okay, it is called as a water of crystallization. This is very important thing for us and for this particular plaster to form the binding effects. Now, if we take this gypsum salt and if we heat it above 393 degree, so above 393 degree Kelvin, what is going to happen is this gypsum will not only lose 3 water molecules, rather it will lose all the water molecules. Okay, it is going to lose the water molecules. So as it loses all the water molecule, there is no water of crystallization left. As a result of which, this will give us an anhydrous calcium sulfate. Now this anhydrous calcium sulfate, what we are receiving, what we have got here, this anhydrous calcium sulfate, it has no tendency to combine with water molecule. It has no tendency to combine with the water molecule. That means it is not going to combine with water molecule. It is not going to give us any hardening effect. So therefore, in short, this particular calcium sulfate is not of any use for us. And so therefore, we also call this thing as dead, burnt, plaster. Okay, so its other name is the dead, burnt plaster. As it is not going to combine with water, no hardening effect is going to take place. So therefore, we call it as the dead, burnt plaster. Correct? So now, as we take a regular plaster, okay, so therefore, as we take a calcium sulfate hemihydrate, we'll observe what happens if we are going to put water to it. As we take this and as we pour water, okay, what will happen is this particular calcium sulfate hemihydrate will take that water along with water of crystallization. It will combine with this. As it takes with the water of crystallization, it changes its structure, the arrangement changes in order to form CaSO4.2H2O. Yes, this is forming back the gypsum. Okay, but here the arrangement of all these particular molecules are very, very important. So therefore, it will form over here an orthorhombic in its packing structure. Okay, so here it is forming orthorhombic in its structure. As we leave it to dry, as it gets hardened up. Okay, so this hardening process, as it hardens, it takes around 5 to 15 minutes in order to get hardened up. Okay, so as it gets hardened up, it will form CaSO4.2H2O, but this time it is going to become monoclinic. Okay, so this particular first step, wherein we are reacting this with water, we call it as the process of setting. Okay, so setting of water over here, calcium sulfate hemihydrate into the gypsum, but the gypsum is in the form of the orthorhombic in the form, and from where it hardens in order to give us calcium sulfate dihydrate, which is again monoclinic in its crystalline structures. So this is the change. This is what we have to remember. Okay. So moving further with the next one, and that is going to be the uses. When we observe about the uses of plaster, the first and foremost use of plaster, as we see in our day-to-day life, is nothing more than in the surgical bandages for plaster in the cases of the broken bones, right? So therefore, that is in surgical bandages for plastering work. Secondly, it is used in casts of statues, in casts work, right? The next one, the next use, as what we can see, is in intensity work. It is also used in ornamental work. Finally, also we see that these particular plasters are used in building industries. Alright, so these are the uses of plaster. Alright, so let's observe one last important compound for today. So, speaking about the next important section, and that is going to be cement. So, when we are taking a look into cement, we prepare this particular cement by a combination of a material which is rich in calcium oxide. We mix this particular material rich in calcium oxide with lime, with clay. Okay, so therefore, as we take this particular cement, the cement is prepared by combining material rich in calcium oxide, right? Along with this, we take into consideration of clay. So, as we mix this particular thing with clay, we heat this. Okay, now, in this particular clay, as we see, in this clay, we get first one, that is SiO2, is nothing more than silica. Along with silica, we get magnesium oxide, we get Al2O3 aluminum oxide, and finally Fe2O3. So these are nothing more than the oxides which are present in clay. Now usually when we take a look into the most important type of cement, and that is called as the Portland cement. Okay, when we observe Portland cement, it has a perfect ratio, it has perfect percentages of various elements. Okay, so that particular percentage ranges as we take into consideration of calcium oxide, it has around 50 to 20%. The next one, as we have, is SiO2. Now this SiO2 is present in 20 to 25%. The next one, Al2O3, which is present in the form of percentage as 3 to 5%, followed by MgO 2 to 3%, Fe2O3 1 to 2%, and finally one more, that is SO3, again 1 to 2%. So this is about the Portland cement. Now, when we observe about the preparations, in the preparation, the material rich in calcium oxide, usually the lime is taken, okay, is mixed with clay, and this thing is heated strongly. As it is heated strongly, it will give us the cement clinkers. Now these cement clinkers are formed once the calcium oxide is fused with the clay. Once it is fused, it yields the cement clinkers. Now, these cement clinkers upon treatment with 2% by mass of cement with we are going to use here gypsum. So 2% by mass with gypsum, it yields us the final one, that is the cement. This is a process, as how we do prepare it. Simple thing, the materials which are rich in the calcium oxide are taken, they are treated with the clay, they are heated strongly. Once it is heated strongly, calcium oxide fuses with clay in order to give us cement clinkers, small little spear-like structures. These clinkers, upon addition with gypsum, 2% by its mass, gives us final thing, that is cement. Okay, so now observing the next details. Taking a look into further details about the Portland cement. So when we take a look into the Portland cement, the first thing is that it contains 3 major components with itself. It is 26% of Portland cement dicalcium silicate, while 51% of tricalcium silicate and 11% of tricalcium aluminate. Alright, so dicalcium silicate, we represent it as Ca2 SiO4, while tricalcium silicate Ca3 SiO5, while tricalcium aluminate Ca3 Al2O6. This is how we have about the Portland cement. That is, as reacts with SiO2, when it is getting fused, it leads to the combination of 2 CaSiO4 dot 3 CaSiO4. This combination is called as dicalcium silicate tricalcium silicate. Right? Now, as we move further, as we see, over here, as the calcium oxide reacts with Al2O3, we have 3 times, that is Ca, 3 times Ca, Al2O3, tricalcium aluminate. As we take a look further, as calcium oxide reacts with Al2O3 plus Fe2O3. Okay, now this particular combination is going to give us CaO dot Al2O3 dot Fe2O3. Now this particular combination is called as calcium It's called as calcium aluminoferrite. Okay, so these are the way the different compositions of the Portland cement are prepared when it is getting fused. Now, one important aspect that we have to understand is, in all the cases, we have used lime. Okay, so therefore, in a cement, the composition of lime serves very, very important criteria. That is, if this particular lime, if the lime that we are using is high in amount, okay, if it is very high, that the required amount, in such cases, this cement will develop cracks in it. Okay, so therefore, it develops cracks. While if the composition of the lime is rather very low, in such case, the cement strength, it gets weakened over time. So we need to understand how much amount of lime that should be used. As we come forward with the setting of cement, that is, whenever we have cement powder and this particular cement powder is mixed with water, upon mixing with water, it will undergo hydration, okay, in order to form a hard mass. Now this particular hard mass is formed on the account of hardening or due to hydrolysis and molecular rearrangement. Now, due to these two particular facts, what is going to happen is that cement which is mixed with water, it gets hardened up. Okay, so therefore these are the two factors which are responsible for hardening of this particular cement. Now, what are the reactions which are going to occur during this setting of cement? First one, as we start with this, with aluminate. So, upon reaction with water molecule, what we have is, as it starts to undergo hydrolysis, due to this hydrolysis process, it will be getting into a colloidal form. 6H2O, and this one gets into a colloidal gel type of form. Right? Now, similar reaction happens when we take into consideration of when it reacts with exporter molecules upon hydrolysis. What we are going to get here is 3CaO dot SiO2 dot X amount of water molecules as water of crystallization, and this one again is going to be formed in a colloidal shell type. Okay, similar reaction happens when we have 4CaO dot Al2O3 dot Fe2O3 plus, when we are going to react this one with water molecule, that is 6 water molecules. So what we get here is 3CaO dot Al2O3 dot Fe2O3 dot 6H2O along with the liberation of Fe2O3 dot CaO. Now again, this entire thing, of course, it is going to form in a colloidal gel form. Okay, at the same time, during these reactions, calcium hydroxide and aluminum hydroxides are precipitated down due to the reactions. Let's observe the reactions now. So, taking into consideration of calcium silicate. Here, as it starts reacting with water, it will form this particular thing. Calcium comes out in the form of calcium hydroxide plus is CaO SiO2. Okay, in order to balance it, let's take over here as 3. So, it is going to form a precipitate. Okay, similarly, when we take 3CaO, Al2O3, okay, upon hydrolysis with 6 photomolecules. So, what we are going to have is CaOH twice plus AlOH thrice. Okay, so in order to balance it, we are going to have here 3 and over here as 2. So, again, what we have is the total amount of precipitate. So, this ends up with the section of alkaline earth metals. Hope you have understood all the concepts. Do take care. We'll meet you in the next video.